Welcome, future medical professionals, to the deep dive. Today, we're embarking on a really crucial journey, a depth dive into the very core of how your body manages all the chemicals that enter it.
From life-saving medications to, well, even the food you eat.
Exactly. And how it keeps everything in perfect balance. Think of it as peeling back the layers on your body's incredibly sophisticated chemical kitchen where substances get transformed,
Uh-huh.
and its essential control tower, which keeps internal conditions perfectly calibrated.
Yeah.
Our mission today is to give you those aha moments, connecting complex science to, actionable clinical insights, stuff that's essential for anyone stepping into a medical career.
Absolutely.
We'll start by untangling how a drug makes its way through your system. Then we'll zoom out a bit to the magnificent world of the endocrine system.
With the special spotlight on the pancreas, it's such a key player.
It really is. So by the end of this deep dive, you'll have a much clearer picture of what the body does to a drug, why that matters for your future patients, and how its internal systems stay stable.
And that connection, between drug processing and the body's own regulation, it's truly foundational. Understanding these processes isn't just about memorizing pathways.
Right.
It's where you'll gain those crucial insights that directly impact patient safety, effective treatment, and honestly, your ability to diagnose. It's about building a robust mental model for how everything works together, like having a master key to unlock those clinical puzzles you'll face.
Okay, let's unpack this then. Imagine your body as a bustling, highly organized city.
So, like that.
When you take a medication, it's like a new visitor arriving, let's say, at the city's chemical customs office.
Right. It needs clearance.
Exactly. Before it can even begin to do its job or eventually leave, it has to go through a series of checkpoints. For you as future clinicians, understanding these checkpoints is absolutely vital. This whole journey is what we call pharmacokinetics. Now, thinking like that city's security chief, what are the 4 major stages every chemical visitor has to pass through? Keep that question in your mind as we outline the journey.
That's a great way to frame it. Pharmacology, as a whole, studies how drugs interact with the body. And within that, we make a clear distinction.
Okay.
There's pharmacodynamics. That's what the drug does to the body. Its effects, its mechanism.
Got it.
And then there's pharmacokinetics, our focus today, which is what the body does to the drug. It's the story of that chemical visitor's journey through the city, so to speak.
So those 4 stages.
Right. To answer your question, those 4 major checkpoints are neatly summarized by the acronym ADME.
ADME. Okay.
Absorption, distribution, metabolism, and excretion.
ADME.
Exactly. Absorption is the drug moving from where you took it into the bloodstream. Distribution is its journey throughout the body to different tissues. Metabolism is the body's chemical transformation of the drug.
Our chemical kitchen work.
Precisely. And finally, excretion is how it leaves the body. Today, our deep dive is really into that crucial M metabolism, the heart of that chemical kitchen.
And what a busy kitchen it is. Most of this chemical transformation, this metabolism, happens primarily in the liver. That's the main processing plant, right?
It really is. But you're right to say primarily. Don't forget, other organs like the kidneys, intestines, even the lungs, they play supporting roles too.
Okay.
But the liver does the heavy lifting.
And the core goal of this kitchen, to take these, foreign substances, these drugs, and tweak their chemical structure.
Exactly. To make them easier for your body to eliminate, it's usually about making them less fat-loving or lipophilic and more water-soluble.
So they can be flushed out, mainly by the kidneys.
That's the general idea. But it's crucial to understand the outcome of this metabolic activity. While most drugs do become inactive or less active,
Which is what you usually want.
right, it ends their effect. But there are critical exceptions. Some drugs are actually prodrugs,
Pro-drugs, meaning?
meaning they only become active after metabolism. Common examples are things like cortisone, which your body turns into the active hydrocortisone, or codeine, which gets metabolized to morphine.
Ah, interesting. So metabolism activates them.
It does. And sometimes metabolism can even make a drug more active than the original compound, like with cyclophosphamide.
Wow, okay.
So the key insight for you here is that knowing a drug's metabolic fate, active, inactive, more active, is absolutely vital for proper dosing and predicting how a patient might respond. It's all about safety and efficacy.
So if metabolism is this chemical makeover, you said it's a 2-stage process, like a 2-step assembly line.
It's a good way to think about it. A 2-step assembly line designed to transform those lipophilic fat-loving drugs into more polar, water-soluble molecules.
And why? just to remind us?
Because water-soluble molecules are much easier for your body to excrete, especially through the kidneys into the urine.
Got it. So phase I.
Okay, phase I metabolism. This is often seen as the preparatory stage in our chemical kitchen.
Off stage. Okay.
In this phase, the body usually adds or uncovers specific functional groups, things like hydroxyl or amino NH2 groups, onto the drug molecule.
What does that achieve?
It makes the drug a little bit more chemically reactive and usually a bit more polar, getting ready for the next step. The most common reactions here are oxidations, basically adding oxygen.
And who's doing this oxidation work?
The undisputed star of phase I, the master artisan, if you will, is the cytochrome P450 system, often just called CYP450 or CYP.
CYP450. Heard of that?
You definitely will. It's a huge superfamily of enzymes, mostly in the liver, and their main job is to introduce these oxygen atoms into drug molecules. They're like a highly specialized toolkit, making these subtle but critical changes.
And here's where it gets really interesting for you, our listeners, thinking about future patients. Out of maybe 60 different CYP450 enzymes, just a handful do, like the lion's share of the work, right?
That's absolutely right. Family CYP1, CYP2, and CYP3 are the major players in drug metabolism. For instance, one enzyme, CYP3A4, metabolizes an astonishing maybe 55% of all commonly used drugs.
55%, that's huge.
It is. Everything from statins to immunosuppressants. And then CYP2D6 handles about 25% affecting drugs like codeine, which we mentioned, and many antidepressants.
Okay, so here's the question I posed earlier, framed differently. If this CYP450 system is like a skilled artisan changing these drugs, what happens if this artisan, say, has a slightly different tool set or skill level from person to person? Or what if their workshop environment changes?
That is the critical question. And it's exactly why understanding CYP450 activity is so central to personalized medicine. There's immense genetic variability in these enzymes.
Genetic variability, meaning people's enzymes work differently based on their genes?
Precisely. Take CYP2D6 again. Some individuals are ultra-rapid metabolizers because they have extra copies of the gene. They clear certain drugs way too quickly.
So the drug might not work well.
Exactly. Or they could be poor metabolizers with reduced enzyme activity, leading to drug accumulation and potential toxicity even at standard doses. This genetic difference means a standard dose could be ineffective for one person and toxic for another.
Wow. That's significant.
Hugely significant. And it's not just genetics. Environmental factors also play a massive role in this artisan's workshop.
Like what?
Well, certain foods or other medications can act as inhibitors, slowing down CYP450 activity. The classic example is grapefruit juice inhibiting CYP3A4, affecting drugs like some statins.
I've heard about that one.
Yeah, or the drug cimetidine. Others can be inducers, speeding up the enzyme activity, things like Brussels sprouts, weirdly enough, or nicotine from smoking.
So diet and lifestyle really matter here.
Absolutely. Even physiological states like pregnancy can alter enzyme activity. For instance, CYP1A2 activity often decreases during pregnancy, which slows down the metabolism of caffeine and paracetamol.
Okay.
So the clinical takeaway for you is crystal clear. Every patient has a unique metabolic blueprint. You have to consider it for safe and effective pharmacotherapy.
So that's phase I, the prep stage, influenced by genetics and environment. What about phase II?
Right. After phase I, many drug metabolites might still be too lipophilic for easy excretion. So they move on to phase II metabolism. We can call this the packaging stage.
Packaging.
Okay. This involves conjugation reactions. Basically, the body attaches a large, very water-soluble group onto those functional groups that were added or exposed in phase I.
Like putting a big shipping label on it?
Kind of. Common additions are things like glucuronic acid, sulfate, or glutathione. This makes the metabolite significantly larger, much more polar, and perfectly ready for excretion, usually via the kidneys into urine.
And is there a main player in phase II, like CYP450 in phase I?
The most common, the reigning champion, you could say, of phase II conjugation is glucuronidation.
Glucuronidation.
Yes, it involves attaching that large water-soluble glucuronic acid molecule. It's incredibly efficient. So much so that some drugs, like morphine, which already have a suitable polar group, can actually skip phase I entirely.
Oh, interesting. Straight to packaging.
Exactly. Straight to phase II glucuronidation before being shipped out. So phase I makes them more reactive, phase II makes them ready for departure.
Okay, this is fascinating. Now, to really bring this metabolism discussion home, let's look at a drug you'll see constantly. Paracetamol or acetaminophen?
Ah, yes. A perfect example.
It presents this really important paradox. If our chemical kitchen, our liver, is so good at detoxifying things, why does something as common as paracetamol become so incredibly dangerous at higher doses? We hear about acute liver failure.
It's an excellent question, and paracetamol metabolism is a classic illustration of how these pathways can become overwhelmed. At a normal therapeutic dose, paracetamol is mainly processed through those phase 2 pathways we just talked about.
So glucuronidation and sulfation.
Primarily, yes. Only a very small amount goes down the phase I route, specifically via the CYP2E1 enzyme. This does form a highly toxic intermediate called NAPQI, N-acetylp-benzoquinone amine.
NAPQI. That sounds bad.
It is potentially very bad. But crucially, at normal therapeutic doses, this small amount of NAPQI is immediately detoxified. It gets conjugated with a substance called glutathione, GSH.
Glutathione. Okay, so that's the key detoxifier here.
For NAPQI, yes. Glutathione essentially neutralizes it, preventing any harm.
So the body has a system in place, but here's the paradox then. Why is there such a critical, potentially fatal difference between taking 1 or 2 pills versus taking, say, a whole bottle? What's the bottleneck in the system that fails?
The bottleneck, quite simply, is glutathione. Your liver only has a finite supply of it.
Oh.
When a toxic dose of paracetamol is ingested, the normal phase 2 pathways, glucuronidation and sulfation, they just get saturated. They can't handle the sheer volume of the drug.
Overwhelmed.
Completely overwhelmed. This forces a much, much larger quantity of paracetamol to be shunted down that phase I pathway via CYP2E1.
Which means
the production of massive amounts of that toxic NAPQI intermediate.
and the glutathione.
The body's limited supply of glutathione is rapidly used up, trying to neutralize this flood of NAPQI. Once the glutathione runs out, NAPQI is left unbound and highly reactive.
And what does unbound NAPQI do?
It wreaks havoc. It's a strong oxidant, causes severe oxidative stress, attacks vital proteins and lipids in the liver cells, and directly destroys hepatocytes, the liver cells themselves.
Leading to liver failure.
Leading to acute liver failure, which can absolutely be life-threatening. The clinical insight here is profound. A protective system, when overwhelmed, becomes the pathway to severe damage.
Which brings us to the critical medical intervention. If someone presents with paracetamol overdose, what do you do?
Time is critical. You administer N-acetylcysteine, NAC, immediately, ideally within 8 hours of ingestion.
NAC, how does that work?
NAC acts as a precursor to glutathione. It essentially helps the liver regenerate its glutathione stores.
Replenishing the bottlenecked resource.
Exactly. By restoring glutathione levels, the body can then neutralize the remaining toxic NAPQI and prevent or minimize further liver damage. It directly targets and resolves that bottleneck. It shows how understanding metabolism literally saves lives.
That's incredibly clear and important. Okay, from prescribed meds, let's switch gears slightly to something equally common, but with its own set of metabolic challenges. Alcohol.
Ethanol. Yes, another substance primarily handled by the liver's chemical kitchen.
And its processing also has some, let's say, toxic twists, especially for liver health.
Indeed, over 90% of the alcohol someone drinks is metabolized in the liver. The main pathway involves a 2-step enzymatic process.
2 steps again.
Yes. First, an enzyme called alcohol dehydrogenase, ADH, converts alcohol, ethanol, into a compound called acetaldehyde. And acetaldehyde is highly toxic.
Acetaldehyde. Okay, that's the first toxic product.
It is. Then a second enzyme, aldehyde dehydrogenase, ALDH, quickly takes that toxic acetaldehyde and converts it into harmless acetate. Acetate can then just enter general metabolic pathways.
So we've got the 2 key enzymes. ADH makes the toxic stuff, ALDH cleans it up.
In simple terms, yes.
But thinking about practical experience, maybe after a few too many drinks. You know alcohol can make you feel pretty rough. So what is the specific toxic molecule that accumulates, causing many of those unpleasant effects? And what's the body's natural defense against it, which, as I recall, can sometimes be lacking?
You're right on track. The primary toxic molecule responsible for many of alcohol's negative effects, from the immediate flushing and hangover symptoms to the long-term liver damage, is acetaldehyde.
Acetaldehyde, got it.
And the body's natural defense, as we said, is the rapid action of ALDH to break it down.
But you mentioned variations.
Yes, and this is clinically very relevant. There are significant genetic variations in the ALDH enzyme. For instance, a specific variant leading to an inactive ALDH2 enzyme is found in roughly 50% of East Asian populations.
50%. Wow. So what happens to them?
For individuals with this inactive ALDH2, acetaldehyde accumulates very rapidly even after small amounts of alcohol. This causes the characteristic alcohol flush reaction, facial redness, nausea, rapid heartbeat. Their defense system against this toxin is basically compromised.
Making them much more sensitive to alcohol's negative effect.
Exactly. But beyond the immediate effects, Prolonged and excessive alcohol consumption has severe long-term consequences, largely due to this acetaldehyde accumulation and the way alcohol metabolism disrupts normal liver function.
How so?
Well, acetaldehyde itself is directly toxic to liver cells. Over time, this causes inflammation and damage, leading to things like elevated liver enzymes you see on blood tests, ALT, AST, jaundice.
Right.
But it also completely throws off the liver's metabolic balance. The process uses up a key coenzyme called NAD plus GOT and produces excess acetyl-CoA. This imbalance leads to several problems,
Such as
fatty liver or steatosis, because the liver starts making more fat and can't export it properly. It can cause dangerously low blood sugar or hypoglycemia, especially during fasting, because the liver can't make new glucose effectively. And it can even contribute to gout, because the altered metabolism increases lactate production, which interferes with the kidney's ability to excrete uric acid.
It's a real cascade of problems.
It really is, all stemming from that initial toxic intermediate acetaldehyde and the metabolic disruption.
Given these serious issues, there's an interesting drug used to help treat alcohol dependence, right?
Disulfiram.
Yes, disulfiram, brand name Antabuse. It works by inhibiting the second enzyme, ALDH.
So it stops the breakdown of the toxic acetaldehyde.
Precisely. So if someone taking disulfiram drinks alcohol, acetaldehyde builds up very quickly, causing a highly unpleasant reaction, severe nausea, vomiting, flushing. It acts as a powerful deterrent.
A clear example of using metabolic knowledge therapeutically.
Fascinating. Okay, we've spent a lot of time in the body's chemical kitchen. Now let's climb up to the management level, the body's control tower, the endocrine system.
A perfect transition.
Yeah.
From processing external chemicals to managing internal balance?
Exactly. We've talked about how the body handles drugs, but this system is all about maintaining internal stability, keeping everything, perfectly calibrated.
And that internal stability is called homeostasis. It's the body's incredible ability to keep its internal conditions, temperature, pH, blood sugar, fluids, within a very narrow optimal range despite external changes.
And how does it do that? What are the components of this control system?
Well, any effective control system, whether it's biological or engineered, needs three core components. First, a receptor, something that acts as a sensor to detect changes or stimuli.
Okay, a sensor.
Second, a control center, usually the brain or specific endocrine glands, which receives input from the receptor, processes it, compares it to a set point, and determines the appropriate response.
The decision maker.
Right. And third, an effector, a muscle, gland, or organ that carries out the response dictated by the control center, aiming to correct the initial change and restore balance.
Receptor, control center, effector. Got it. So let's put this control tower into action. Imagine you've just run a marathon. Your body temperature is soaring, way above its normal set point. Which type of feedback loop kicks in to cool you down, and who are the key players, the receptor, control center, effector in that scenario?
That's a classic example of a negative feedback loop. This is the most common and essential type of control in the body.
Negative feedback. Why negative?
Because the response opposes or negates the initial stimulus. In your marathon example, the rising body temperature is the stimulus. Thermoreceptors in your skin and brain, those are the receptors, detect this increase.
Okay.
They send signals to the hypothalamus in the brain, that's the control center. The hypothalamus compares this high temperature to the normal set point and activates effectors like sweat glands to start sweating and blood vessels near the skin to dilate, releasing heat.
So sweating and flushed skin cool you down.
Exactly. As the body temperature drops back towards the set point, the stimulus decreases and the hypothalamus switches off the sweating and vasodilation. The response counteracted the initial change. It works just like your home thermostat turning off the AC when the room cools down.
Makes sense. What about positive feedback?
Positive feedback loops are much rarer. Here, the response actually enhances or exaggerates the original stimulus. They often lead to rapid, escalating changes and are usually involved in processes that need to be completed quickly, like blood clotting or the hormonal cascade leading to ovulation or childbirth. But for moment-to-moment stability, negative feedback is king.
Okay. So how does this control tower, these control centers, communicate their commands across the whole body?
Primarily through hormones. These are the body's chemical messengers.
Chemical messages.
Produced in specialized endocrine glands, they travel through the bloodstream to target cells or organs elsewhere in the body, carrying instructions.
And how do they work? Just locally or?
They can have different ranges of effects. Endocrine effects are the classic ones. Hormones travel via the bloodstream to act on distant target tissues. But there are also paracrine effects, where a hormone diffuses locally to affect neighboring cells,
Okay.
and even autocrine effects, where a hormone acts on the very same cell that produced it,
Interesting. And they travel fast.
surprisingly fast. Hormones released into the blood can reach essentially all parts of the body within about 30 seconds. Their specific effect, though, depends entirely on whether the target cell has the right receptor for that hormone and the concentration of the hormone itself.
And these hormones, they're all chemically similar?
Not at all. They come in various chemical flavors. Some are derived from single amino acids, others are peptides or larger proteins, some are glycoproteins, proteins with sugars attached, and some are steroid hormones derived from cholesterol.
Does the chemical type matter?
Hugely. A hormone's chemical structure dictates everything. How it's synthesized, whether it can be stored, how it travels in the blood, alone or bound to proteins, how it interacts with its receptor on the cell surface or inside the cell, and how it's eventually broken down and inactivated.
And the glands producing them, we have the pituitary, thyroid, adrenals.
Exactly. Pituitary, thyroid, parathyroid, adrenals, gonads, ovaries, and testes, and crucially, for our discussion on metabolism, the pancreas. Which brings us neatly to our next focus.
Perfect. Let's zero in on that organ, the pancreas. You called it a master of both digestion and metabolic control earlier. It seems to play a role in both the chemical kitchen and the control tower.
It absolutely does. It's a fascinating dual-purpose organ. The vast majority of it, maybe 98%, has an exocrine function,
Exocrine meaning?
meaning it produces substances, in this case digestive enzymes, that are secreted through ducts into the small intestine to help break down food.
Okay, that's the digestion part.
Right. But it's that crucial remaining 2% that handles its endocrine role, secreting hormones directly into the bloodstream.
And where does that happen?
This happens in specialized clusters of cells scattered throughout the pancreas called the islets of Langerhans. Think of them as tiny hormone islands within the main pancreatic tissue.
Hormone islands. I like that.
And within these islets, there are different types of cells, most importantly the alpha cells and the beta cells, each producing a different key hormone.
Okay, so thinking back to that internal thermostat idea, but this time for blood sugar, which is absolutely critical in clinical practice, what are the two main switches produced in these islets that crank blood sugar up or turn it down, and how do they work together?
The two main switches, the absolute key players for blood glucose control, are insulin and glucagon.
Insulin and glucagon.
They are truly the yin and yang of blood sugar regulation.
Oh.
Insulin, which is secreted by the beta cells in the islets, primarily acts to lower blood glucose levels, especially after a meal.
Okay, insulin lowers glucose.
And glucagon, produced by the alpha cells, acts mainly when blood glucose is low, between meals or during fasting, and its job is to raise blood glucose levels.
Glucagon raises glucose. Opposing actions.
Exactly. They work in this continuous, elegant, opposing dance to maintain blood glucose within a very tight normal range. Homeostasis in action.
Let's dive into insulin first. It's so central to conditions like diabetes. How is it made and released?
Right. Insulin synthesis is quite a process. It starts as a larger precursor molecule called preproinsulin, which is then processed to proinsulin. Finally, proinsulin is cleaved into the active insulin molecule and another fragment called C-peptide.
C-peptide, is that important?
Clinically, yes, because insulin and C-peptide are packaged together in secretory vesicles and released in equal amounts. Measuring C-peptide levels can be a useful way to assess how much insulin the patient's own pancreas is producing, even if they're receiving insulin injections.
Ah, clever. And what triggers the release?
The main trigger is high blood glucose, like after you eat carbohydrates. Glucose enters the pancreatic beta cells through a specific transporter called GLUT2. Inside the cell, glucose metabolism generates ATP, the cell's energy currency. This rise in ATP causes specific potassium channels on the cell membrane to close.
Closing potassium channels, what does that do?
It changes the electrical charge across the membrane. It causes depolarization. This depolarization then opens voltage-gated calcium channels. Calcium ions rush into the cell.
And that's the trigger.
That influx of calcium is a direct trigger for the stored vesicles containing insulin and C-peptide to fuse with the cell membrane and release their contents into the bloodstream. It's called exocytosis.
Wow, quite a cascade. Glucose in, ATP up, K plus channels closed, depolarization, C2 plus in, insulin out.
You got it. And understanding that cascade is key. For example, a major class of drugs used to treat type 2 diabetes, the sulfonylarias, work by directly closing those ATP-sensitive potassium channels, mimicking the effect of high glucose and stimulating insulin release.
Fascinating link. Okay, so insulin is released. What does it do?
Once in the bloodstream, Insulin travels to its target cells, primarily skeletal muscle, liver, and adipose tissue, fat cells. There, it binds to a specific receptor on the cell surface, called a tyrosine kinase receptor.
Tyrosine kinase receptor.
Binding activates the receptor, which then triggers a complex signaling cascade inside the cell. This cascade leads to several crucial anabolic effects, meaning effects that build things up or store energy.
Anabolic, like building muscle.
In a way, insulin promotes the uptake of glucose from the blood into muscle and fat cells by causing another transporter, GLUT4, to move to the cell surface. It stimulates the liver and muscles to store glucose as glycogen. We call this a glycogenic effect.
Storing glucose. Makes sense.
It also inhibits the liver from making new glucose from other sources, an anti-gluconeogenic effect. It stops the breakdown of fat, an anti-lipolytic effect. And it increases protein synthesis.
So it's basically the hormone of plenty, telling the body to take up nutrients and store energy.
That's an excellent way to put it. It's the primary hormone that lowers blood glucose after a meal by promoting uptake and storage.
Okay, clear. Now, flip side, glucagon, the yang to insulin's yin.
Exactly. Glucagon is released by the alpha cells in the pancreatic islets, primarily when blood glucose levels start to drop too low.
So, opposite trigger to insulin.
Right. It's also synthesized as a precursor protein and then cleaved to the active form. Its main targets are the liver and, to some extent, adipose tissue.
Different receptor.
Different receptor type, yes. Glucagon binds to a G-protein coupled receptor, GPCR, on the surface of liver and fat cells.
GPCR, very common type.
Very common. Binding activates an internal signaling pathway that primarily increases the levels of a molecule called cyclic AMP, or CAMP, inside the cell. This CAMP then activates other enzymes.
In the overall effect, you said it raises blood glucose. How?
Its effects are generally catabolic, breaking things down to release energy. In the liver, glucagon strongly promotes the breakdown of stored glycogen back into glucose, a glycogenolytic effect.
Releasing stored glucose.
Yes. It also stimulates the liver to make new glucose from amino acids and other precursors, a gluconeogenic effect. And in adipose tissue, it promotes the breakdown of stored fat, a lipolytic effect, releasing fatty acids that can be used for energy.
So it's mobilizing stored energy to keep blood glucose up between meals or during fasting.
Precisely. It counteracts insulin's effects to prevent hypoglycemia, low blood sugar.
And when this delicate balance between insulin and glucagon gets disrupted, that's where we see problems.
That's exactly right. Problems like chronic hyperglycemia, high blood sugar, and diabetes mellitus, resulting from either insufficient insulin production, type 1, or the body's cells not responding properly to insulin resistance, typical of type 2. Or, conversely, problems with hypoglycemia if glucagon response is impaired or insulin levels are too high. It really highlights how critical this pancreatic control tower is for overall metabolic health.
Okay. For you, our listeners, future medical professionals, this is really where it all ties together, isn't it? We've journeyed through the ADME process, understanding how your body's chemical kitchen transforms drugs.
Thinking about Phase 1's CYP450 Master Artisans and Phase 2's packaging step.
Right. We uncovered that critical difference between safe and toxic doses of paracetamol, pinpointing that glutathione bottleneck.
And the life-saving role of NSC.
We explored alcohol's metabolism, identifying acetaldehyde as the key toxin, and seeing how genetic variations in ALDH matter.
And the long-term liver and metabolic consequences.
And then we climbed into the body's control tower, the endocrine system, witnessing that elegant opposing dance of insulin and glucagon, keeping blood sugar steady.
What's truly fascinating, and what you need to take away, is how deeply interconnected these systems are. You can't think about drug metabolism in isolation from, say, endocrine function.
How so? Give us an example.
Well, think about treating a patient with diabetes. Their baseline hormone levels and metabolic state are already altered. How might that affect their ability to metabolize other medications you prescribe? Or how might a drug affect their blood sugar control? Understanding both the chemical kitchen and the control tower is essential.
And it brings us back to that idea of personalized medicine.
Absolutely. Every patient's unique chemical blueprint, their genetics affecting CYP enzymes or ALDH, their diet, their lifestyle, their underlying conditions like diabetes, means there's rarely a true one-size-fits-all approach to pharmacotherapy.
So, as you step into your medical careers, here's something to think about. If every single patient has a slightly different chemical kitchen and control tower, how will you approach personalizing medication dosages and treatment plans? How will you use this knowledge to avoid toxicity and really maximize the benefit for each individual?
And looking forward, What new diagnostic tools might emerge in your professional lifetime? Could we one day have rapid tests that map a patient's specific metabolic blueprint, their key CYP activities, their glutathione levels, allowing for truly precise, individualized medicine right from the start?
Food for thought indeed. Thank you for joining us on this deep dive into the body's intricate processing and control systems. Keep exploring this fascinating interplay.
Your future patients will definitely thank you for it.